All right, so in this lesson, what we are going to be discussing is getting into simple and compounding interest. This is what logarithms and exponents are primarily used for in financial transactions. This is where we would be looking at something like if we're making an investment to see how much time it would take to get a certain return, or how much money we would have to pay back over a course of time. Now, there are common variables that we're looking at here. I, interest, the lowercase p is principal, lowercase r is the interest rate written as a decimal. So let me say, so let's say we had 7.5%. Well, as a decimal, that would be 0.075. So keep that in mind when you're doing your work. And t is time in years. So simple interest formula, P times the rate times the time, that would be telling you what the interest would be. Now, there's a variety of uh, formulas that are available to us. And what we're going to be looking at here is, well, which formula are we going to use kind of depends on, well, what words are being used to describe the problem that we're talking about. There's certain key words that we're going to look at here. So here, accumulated value using simple interest. Okay, so simple interest would kind of be a key word that we would look at. And there's two forms where P is in both of the terms that we would have, or the right side where P is kind of factored out. Personally, I prefer that form. That's just a personal preference, nothing against the other one. If you want to use it, by all means. So here, accumulated value using interest compounded yearly. So here, keywords, interest compounded yearly. If we see that in our word problems, well, that kind of lets us know, hey, we might want to take a look at that one. Okay, so when we're looking at the words, or when we're reading the word problems, I should say, we really want to kind of see, well, what are my keywords that we want to take a look at? So that is going to really tell us what formula that we're going to be using. Now, for those of you that may be watching this outside of like a normal classroom environment, if you need this presentation, because I'm providing this in class so that way it can cut down on the time it takes to write out the notes for our for your own study purposes. I have attached the presentation in my website where the video is located at the bottom of the page, so you can get this and download it for yourself, so that way you don't have to necessarily write everything down if you're trying to use this to take notes. So here, accumulated value using interest compounded in N times per year. There's kind of a key thing there. Now, this particular function, this is a big time player here, as far as this is how kind of the number E was derived using a formula like this. This is really going to be used a lot when dealing with interest rates, because there's lots of different ways that we could compound things. We could compound things annually, which would be, 1 year. Semi-annually would be 2 years. Quarterly would be 4 times a year. Monthly would be 12 times a year, and so on. So depending on when it's compounded or how often it's compounded, that really has a role in how much money is either owed or needing to be given to somebody. So this particular equation, this is going to be one that gets used a lot in application problems, but we won't necessarily use it all the time, but it is used a lot of the times. So when we are trying to solve an equation, or to solve an application problem like what we're going to be looking at, we really need to kind of see, well, which problem are we going to be using? Which formula are we going to use? And based on the way we determine that is by reading the problem and see, well, how is it compounded? What are we looking for? There's certain key words that we'll see in the problem itself that will allow us to kind of determine which formula that we're going to be using. Once I know that, then we're going to use a lot of the practice problems that are, or a lot of the skills that you've normally done solving an equation. We're still going to try and isolate what we're working with using opposite operations. And then we might need to take the log of both sides. If the variable that we're solving for is in the exponent position, it really just kind of depends on which formula that you're using to see which equation, or to see what skills you're going to be using. So here's our first example. Now again, the presentation is being provided to everybody in class so that we can kind of cut down on the time it takes to write this stuff out. And if you're not in class watching this and you need a copy of it, it's at the bottom of the page where this video is located. So when we're reading the problem here, okay, so Lori has a new business that she opened up in a strip mall. So she borrows $50,000 from a group of investors at 4.55% simple interest. Okay, here's some key words that we're looking at as far as something in the problem that's really going to let us know, well, what equation, what formula out of those ones that we saw, which one are we going to have to use? Now, there's definitely other things in here that we want to kind of identify. So the $50,000, this is our principal amount that is being borrowed. The 4.55% interest, that is the rate, the interest rate that they're borrowing the money against. Okay, and so finishing it off, okay, so the business is booming, and it takes them less time to pay off the bill, to pay off the debt than they thought it would, so they wound up paying back $62,500. So this would be the amount that needed to be paid back based off of the principal that was borrowed and the interest rate. And what it's asking us to do is, how long, how much time did it take? So out of the things that we have, first of all, the key words in the problem that lets us know what formula we're going to be using is the simple interest. Okay, so there is a formula for simple interest, which is A is equal to, this is the one that I said I had a preference for, P times 1 plus the rate times the time. So by identifying the keywords simple interest in the problem, that lets us know, well, that's the formula that we want to use. And reading the rest of the problem, now we've been able to identify, okay, these are the things that we're putting in. So how long? That is the time that we're looking for. So we've identified certain things in the word problem. Now that we can substitute those into the formula and then solve for our missing variable. So A, the amount that was paid back was $62,500. The principal amount that they borrowed was $50,000, and one, now the rate is 4.55%, so when we convert that to a decimal, we would say 0.0455. Just divide 4.55 by 100. And time is what we're looking for. That's the one thing that we don't know. How long did it take to pay that off? Now, this is a fairly basic equation. There's nothing to do with the exponents or logarithms here because none of the variables are in an exponent spot. So there's no reason for us to have to convert anything to a log. This is straight, pure, just basic algebra 1 material. Just solve for t in this case. So take everything that's not t and move it away. So the first thing I'm going to do, divide by the 50,000 from the right side. And the 50,000 on the right side simplifies to be 1. So $62,500 divided by $50,000 simplifies to be 1.25, and that will be equal to the remaining stuff in the parentheses. But since the 50,000 is gone, we no longer need to write the parentheses. So we just have 1 plus 0.0455. 0.045t. Move the 1 over through subtraction, and I get 0.25 to be equal to 0.0455t, and then divide both sides by the 0.0455, and the time would be about I'm writing it wrong, 5.495 years, but I think that's close enough to say that we could probably say about 5.5 years for time. So they borrowed $50,000 for 0.55% interest rate. So if they paid back $62,000, it took them about 5.5 years to pay off their loan. Not too bad, actually, considering the amount of money that was borrowed. So here, our next example, okay, for an account where the interest is compounded annually. Okay, so here is a key word, compounded annually. If you refer back to the formulas that were provided at the beginning of the presentation, that is a key word that lets us know what formula that we're going to be using. So it says, okay, we're compounding something annually, and it wants us to know what is the principal. So that is P, that's what we're looking for. What's the principal needed to accumulate? Okay, there's the A, $30,000, 146 at an interest rate. So here's R, and 7, that would be time. So the formula that corresponds to the keywords of something being compounded annually is this. P is equal to A over, in parentheses, 1 plus R to the T power. Okay? Now, this one very well could mean that, hey, because we do have something in the exponent position, maybe we would need to do something with logs. But let's see what we're looking for. It's asking us to find the principal. So we're not looking for anything that needs us to do anything with an exponent or a log. Because the only thing in an exponent position is time, and they gave us that. So it says, what is the principal amount? Meaning they gave us everything on the right side of this equation. So the accumulated amount is the $30,146. The rate as a decimal will be 0.053, and the time is 7 years. So this one is a fairly straightforward problem. All you have to do is just plug the stuff into your calculator and see that the principal amount that they would need would be right about $21,000 and change, 57 cents. So pretty much $21,000. So there we go. But a fairly straightforward problem. But again, we really need to read the question to say, okay, what keywords are being provided to allow me to determine what formula to use, and then find what is represented where, and then the rest of the problem as far as, what's the interest rate, what's the time, and am I looking for the accumulated value or the principal value. So here, this will be our kind of last example here for simple interest. What we're going to be looking for when we read the problem again is what kind of keywords will allow us to determine what formula to use. And then once I know kind of the formula to use, well, what values in that formula did they give me as far as interest rate, principal amount, stuff like that. Now here, I know they're talking about Swiss francs, but I'll probably still just use a dollar sign and stuff because I really don't know what a symbol for a Swiss franc is, but I know what a dollar symbol is. So Helen invests 6,000 Swiss francs in a college saving plan to pay for her dollars for share of college 18 years from now. She estimates 25,000 francs will be needed at an interest rate of 7.2%, compounded daily. There's the key word that I'm looking for, compounded daily. Now, out of the formulas that we had, there's only one formula that talks about anything being compounded daily, and that is this formula. A is equal to P, and in parentheses we have 1 plus R over N to the NT power. That was the big player that I told you to get used a lot in problems like this because of the fact that it has such a variety of ways to compound things. So now let's go back over the problem. Okay, well, what do we have? We still have a P, R, N, and a T for time. Okay, so 18 years, there's time. 25,000 francs is what's needed. So that 25,000 francs, that is the accumulated amount that we might be looking for. 7.2% would be the rate, okay? And they're starting off with $6,000, so there's your principal amount. Now, the part A of the question says, will she meet her investment goal of 25,000 francs if she invests 6,000 francs for 18 years at 7.2% interest rate compounded daily? Okay, and there's another key word there. That is going to be in, and daily would be 365 in this case. So let's do part A here. So the formula says the accumulated amount is equal to the principal multiplied by 1 plus the rate over the compounding amount to the compounding amount and time as an exponent. So the goal is trying to get 25,000 francs, and that's what we're looking for. Now I can tell you just by the way the problem is set up, will she meet her goal? And part B says if not, well, part A probably says no, they're probably not going to meet their goal. But let's go ahead and see what the numbers tell us. So we have 6,000 francs as our principal amount. The rate as a decimal will be 0.072. And in this case, because we're compounding it daily, will be 365. So we will say 365 in the exponent position 2, and the time in this case is 18 years. So this is a fairly straightforward one. You just plug this stuff into your calculator using your keystrokes. Pardon me. And here we will see that at 6,000 francs invested at 7.2% interest rate for 18 years compounded daily will give us, and again, I don't know what the symbol for Swiss franc is, 22,717 francs and 49 parts of a franc. I don't know if they have cents like that, what they would call it in Swiss or Switzerland. But so unfortunately, no, they're not going to reach their goal of 25,000 francs in this case. So part B says, okay, well, if they don't meet their goal, surprise, surprise, they didn't, find the minimum rate of interest that will enable her to meet their goal in 18 years. So they can't, apparently, can't afford more than 6,000 francs to begin with. And the time, obviously, well, if you're going to start college in 18 years, the time can't change. So really the only thing that we have to worry about here would be the compounding rate or the interest rate. And compounding daily, it's about as much as you can compound something before we get into something known as continuous compounding. So the only thing that we can change here is the interest rate. So we know the accumulated amount should be 25,000 francs. We're still investing 6,000 francs initially. The rate is what we do not know. The time of compounding is still 365. And so we're still going to be doing it for 365 days for 18 years. So now we need to solve this equation in terms of R. What is the rate going to be? So straight away, I'm going to divide both sides by 6,000. So 25,000 divided by 6,000 unfortunately doesn't work out to be a very nice decimal. So I don't want to write that as a decimal. However, 25,000 over 6,000 does simplify to be 25 over 6. So that will be left with, and I still need to keep everything in parentheses for the time being because it is still raised to an exponent, and 365 times 18 is 6,750. Now, so here we're at the point where, okay, the variable that we're solving for is inside of my parentheses. And I have to get rid of, or I have to do something with that exponent of 6,750 in order to get rid of the parentheses and be able to solve for r. Now, I can tell from experience that some students are going to look at this and say, well, I have no idea, Mr. Piercy, how to get rid of that 6,750 in the exponent position. And I would say, aha, I think you do. You're just not thinking big enough. So, or maybe small enough. If I said 8 was equal to x squared. Now I know 8's not a nice number to take the square root of, but we have experience of getting rid of an exponent, and in this case we would say take the square root of both sides. Well, in our process of studying exponents and logarithms, one of the things that we learned about exponents is that instead of saying the square root, saying the square root of something is the same thing as saying something to the 1/2 power. So what I would do to get rid of the 6,750 in the exponent's position would essentially be to take the 6,750th root of the stuff on the right side. Or a cleaner way of doing it would be to say, well, let's take the 1 over 6,750th power, because that's the same thing as a root. But of course, if I do it to one side, I have to do it to the other side. And I'll kind of squeeze it in here because we're so used to seeing it on the right side. Okay, so on the right side of the equal sign, just like anything else, if I tried to undo a square with a square root, they cancel each other out. Well, this and this, that would just simplify to be an exponent of 1, and an exponent of 1 really doesn't matter anymore. So we have the 1 plus the r over the 365 without the parentheses anymore. And unfortunately, 25 over 6 wasn't a nice decimal number to begin with, and if I raise that to the 1 over 6,750th power, it still isn't a very nice number. So I'm going to keep it as the way I have it written, 25 over 6 to the 6,750th power over 1, or under 1, like that. And now it's a relatively simple process of moving the 1 over through subtraction. So let me write this again, 25 over 6 to the 1 over 6,750th power minus 1 equals r over 365. And now we would multiply both sides by the 365 to get r by itself. So I would have 365 times 25 over 6 to the 1 over 6,750th power minus 1 to be equal to the rate. And that's what we would wind up having to type into our calculator to figure it out. And you may need to practice it a couple of times just to make sure you get the number correct. But here what we would say, and I'm really kind of running out of room, so let's bring it up here. The rate in this case would be 0.077, and I'm going to just round it off there. I know the number continues as a decimal, but we have to round it somewhere. So that would be 0.077, or as a percentage, 7.7%, and that's really what we would be looking at. So instead of 7.2%, we would really need it to be about 7.7%. So now there are more obviously more examples that we could probably come up with and demonstrate here, but as long as you practice identifying what are the keywords to tell me what out of those formulas are we going to use, and then correctly identifying the rates, the principal amounts, etc., you should be in pretty good shape. But if there are questions about anything that you saw in the video, please make sure you make a note of them. Write them down and address them to me when you see me in class or when you come to tutoring. But this is going to kind of conclude the presentation here about how we will apply the formulas for simple interest. But again, thanks for watching. If you have any questions, let me know, and we'll see you soon.